Hello, Chem 1A. This is Chapter 6, Lecture Video 8, and we're going to be discussing a little bit more about enthalpy. So we learned how to calculate the enthalpy of a reaction in the last lecture video using the products minus the reactants of our reaction and the standard enthalpies of formation. We got to understand one important part about enthalpy. It's really defined as the amount of heat transferred in one particular amount of reaction occurring. And that amount is 1 mole of reaction has occurred. And so we can use this relationship to calculate how much energy will be given off in a very specific reaction with a very specific amount of reactants present. So if we have this reaction, which I think this is actually sucrose, which is sugar, so this is like a combustion reaction of sugar. It has a delta H of about negative 5,645 kilojoules per mole. Now this per mole here is per mole of RxN, how many reactions occurred. In this case, 1 mole of reaction will produce about a release of 5,645 kilojoules of energy. But what if we don't have a mole of reaction occurring? What if we have excess oxygen, right? This is an excess. And we only have about 3.5 or 0.5 grams of the C12H22O11. How much energy is going to be transferred in this scenario? Well, the first thing we need to do is we need to get rid of this mole component, and we can do that by taking this grams of C12H22O11 and converting that to moles. All right, so I know 3.05 grams of C12H22O11 has a molar mass of about 342.34 grams of C12H22O11 per 1 mole of C12H22O11. Now, this obviously will cancel grams, and then we'll be left with moles of this compound, but that's not actually moles of the reaction. That's moles of a specific reactant, in this case, in the reaction. So how do I get from here to moles of reaction? Well, it's pretty simple. We put 1 mole of RxN in the top, and always 1 mole when we want to get to moles of reaction, because we know how many moles each thing is formed and reacted based on the balanced chemical equation for one reaction, right? So I know that 1 mole of C12H22O11 reacts in this reaction, since we have a 1 here that's not shown. If this was oxygen, we would put a 12 here. If it was CO2, we'd put a 12 there. If it was H2O, it would be 11. It doesn't matter which substance we're talking about in the problem. We just use their stoichiometric coefficient in the denominator to cancel out the moles that we have and go to 1 mole of reaction in the numerator, and this gets us moles of reaction, which is what we need to solve how much energy is going to be released in this reaction. So in this case, we get 0.008909 moles of reaction. And at this point, I just need to get the moles in our delta H here that we were given to cancel out. So I know that negative 5,645 kilojoules of energy per 1 mole of reaction times 0.008909 moles of reaction. The moles of reaction are going to cancel out, and we're just going to be left with kilojoules, which is an amount of energy. So that gives us our answer here, and we get that in this reaction, negative 50.3 kilojoules of energy are going to be released. The released comes from the fact that it's a negative value. All right, so this is another example problem that we might have with enthalpy calculations. Let's look at some more. Now, we need to understand some of the rules with enthalpy in order to do this. Now, if we change something about our reaction, our delta H of that reaction is going to reflect that change. So there are 3 rules about this and 3 ways we can change our reaction. and therefore 3 ways that will change our enthalpy value. Our first way is if we so-called flip a reaction. What I mean by this is if I take this reaction, for instance, carbon reacting with oxygen gas to go to CO2, this has a delta H of negative 393.5 kilojoules, technically per mole, but sometimes we leave off the moles. At the end of the day, if I flip this, what I mean is I'm basically going to switch the products and the reactants. Something like this, right? So now if we look at the differences between these two reactions, in this case CO2 was a product, now it's the reactant. These were the reactants, now they're the products. And we want to know what the delta H of this reaction is. Well, the rule here is that if we flip the reaction, we got to change the sign of the delta H, and that's it. So in this case, the reaction had a negative delta H, but since we flipped this reaction, its delta H is simply going to be positive 393.5 kilojoules per mole. All right, so let's look at another rule. If the reaction is multiplied by some value, then we need to also multiply the delta H by that value. For instance, same reaction that we had in the last slide, we have carbon reacting with O2 to give me CO2. What if I wanted the delta H for 3 carbons reacting with 3 O2s to give me 3 CO2s? Well, in this scenario, the difference between these two reactions is the second reaction is times 3 of the first one. This means that to get the delta H of that reaction, I just need to take my negative 393.5 kilojoules and multiply it by 3. This will give me a value of about, I think, 1100 kilojoules, give or take. Yeah, so we should get about 1180.5 kilojoules for our delta H of this reaction. If we multiplied by 2, it would have been the delta H multiplied by 2. It all just depends on what change is occurring between the two reactions. All right, so let's talk about the last rule, and that is really known as Hess's law. If we carry out a reaction in a series of steps, delta H for the overall reaction will be equal to the sum of the delta H's for each individual step. And what I really mean by that is if I add two reactions together, like here, if I add these two together, notice that some of the NOs cancel and the O2s cancel because they're on opposite sides of our reaction arrow. Now the O2, there's going to be some left over because we had 3 halves of an O2 on the reactant side of the first reaction and only 1 O2 on the product side of the second reaction. So we end up with two NO2s react with 1/2 of an O2 to give me N2O5. And if we wanted to calculate what the delta H of this reaction is, the rule is we just add the two delta H's of the reactions that we added together to get this reaction. So in other words, if we add those two values together, we get that our delta H of this new reaction is negative 109.5 kilojoules per mole. Now, typically we don't use these rules individually like I'm showing as an example for each one. We use them all at once, and where we can use these often is where we want to determine the delta H of a specific reaction and we know the delta H's for other reactions. For instance, let's do an example problem. So we want to determine the delta H of this reaction here by taking these four reactions, and combining them to give me 4 reactions that will add together to give me that one. Now we need to do this through manipulation of each individual reaction, possibly flipping it so that it's opposite sides, possibly multiplying it by a value, and all that depends on getting this final overall reaction that we are given up here. Now, I like to use that first reaction, the one we're trying to solve for, as a guide. I kind of think of these problems as like puzzles, and we need to rearrange the puzzle pieces so that they all fit together and give us this final equation. Now, how do we do that? Well, we're always referencing to keep using my analogy, the front of the puzzle box, or in our case, the reaction that we want to determine. So the first thing I'm going to do is I'm going to try to find a reactant or product in my reaction I'm trying to solve for that's only in one of these four reactions. And I can do that with two substances at least. I noticed that P4H10 is only in the second reaction here. I noticed that Cl3PO is also only in this reaction. And I can also see that PCl5 here is also only in this reaction. So this gives me some guidance to what I need to do. So if we look at this first one, P4 reacting with 5O2 to give me P4O10, the first thing I notice is that P4H10 in this reaction is a product, but in my overall reaction, it's a reactant. So the first thing I'm going to do is I'm going to flip-flop this reaction. So I'm going to rewrite it right now. So we have P4O10 solid going to P4 solid plus 5O2 gas. Now by flipping this, I've changed the delta H of this reaction, right? I need to change its sign specifically. So this is going to be equal to positive 2067.3 kilojoules per mole, technically. Now, great, let's look at the next one. So here, I notice that PCl5, again, is on the product side, but over here in my final reaction, it's on the reactant side. So again, I'm going to flip-flop this reaction, right? So PCl5 gas goes to PCl3 gas plus Cl2 gas. And if we think about this, that's not all I need to do, because the other issue I have is that PCl5 here has a 6 in my overall reaction, whereas in this reaction it's a 1. So what I need to do here is I need to multiply this whole reaction by 6 so that I have a 6 in front of PCl5. This gives me my new delta H. Now, in order to get this delta H, I had to flip the reaction. So the reaction is going to now be positive instead of negative, right? We originally had a negative value here. It now needs to be a positive value because we flipped it. And I need to multiply it by 6 because I multiplied the reaction by 6. So negative 84.2 effectively gets multiplied by negative 6. This gives me positive 505.2 kilojoules per mole. All right, so now let's look at that last reaction. Not the last reaction we're going to talk about, but definitely the last reaction in the set of 4. We have Cl3PO, and that is in both the product side here and the product side here. So this is a reaction we do not need to flip because we have Cl3PO on the right side. However, there are 10 Cl3POs in our final equation, so I need to multiply this entire reaction by 10. This gives me 10 PCl3s, gases, plus 5 O2s, goes to 10 Cl3PO gases. And my delta H here of this reaction is just going to be equal to the original, the negative 285.7 times 10, or in other words, negative 2,857 kilojoules per mole. So we haven't used that first equation yet, and if we look at why, there's an important reason. Now, we may have all the products and reactants in our overall reaction, the one we're trying to determine, all the way up here, but we also have some other stuff that's going to be left in our equation. For instance, if we look at this, right, we have Cl2 in this reaction here, but it's nowhere else in our problem. So when we add these together, the Cl2 is going to stick in the reaction, but it's not going to be, it's going to be in the overall, but we don't want it in the overall because there is no Cl2 in this reaction up top. So I need to use this equation here, the first one that we were given, to cancel out the terms that I don't want in my overall. Another example is the P4 solid. It's in the overall reaction right now because there's nothing canceling with it. And if I want it to cancel, it's on the product side here. So that means I need this P4 on the reactant side, and there's one of each. So we're just going to rewrite this as written in this case. And this goes to 4PCl3. And the delta H here of our reaction is just the same value we were given, negative 1225.6 kilojoules per mole. All right, so let's look at what happens when we add these reactions together. All right, so if I add these together, I notice the P4s, they're going to cancel. I notice the 6Cl2s, they cancel because they're, again, everything on opposite sides of the reaction arrow is going to cancel out with each other. I have these 4PCl3s here, and they're with this 6PCl3s going to cancel with these 10 PCl3s because 4 plus 6 is 10. So we have 10 PCl3s on the product side and 10 on the reactant side. They cancel out. These 5O2s cancel with these 5O2s. And what we're left with, if we look, is just going to be this 10Cl3PO, the P4O10, and the 6PCl5. So my final equation here is this guy. And if we look, this is exactly the reaction we're trying to determine up here. So now my delta H of this reaction is just the sum of all these delta H's. So delta H here of this reaction is equal to negative 610.1 kilojoules per mole. And again, I got that value just by adding the 4 delta H's we had manipulated because we added their equations together. All right, so this is a pretty typical example problem for this type of situation. So if you have any questions, let me know. As always, I'm available via office hours or email, and we can schedule a Zoom meeting.